Alright, hi everyone. Continuing with our data structures and algorithm series, in our previous video, we saw how quicksort works and its implementation in JavaScript. And now we are going to see the time and space complexity of quicksort. Now before directly jumping onto the time and space complexity, let's recap how quicksort works in short. If you remember the definition, in quicksort we have to select one element at a time, calling it pivot, and then moving all smaller elements to the left and all larger elements to the right of the pivot. And we have to recursively do this process until we cover all the elements of our array or the given data. If I quickly show you the example again, then you can see I have an array here with few elements, and for simplicity I am taking the first element as my pivot. Now as per the definition, we need to move all the smaller elements to the left and all the larger elements to the right hand side. And once we do that, our array will look something like this, right? And we need to continue this process until we sort our given data. You can see I'm selecting 0 as my pivot now, and since there are no smaller elements than 0, so there will be no change. Moving on to the next, selecting 2 as my pivot, and then we see 1 is smaller than 2, right? So we have to move it to the left hand side. And after doing that, we can see 2 is also sorted. And same process we will continue until our array is sorted. So that's how quicksort works. If you want to see it in detail and want to see how we implement it in JavaScript, you can refer to my quicksort video. I will attach the link in description. Now quickly coming back to the time and space complexity. If we talk about the best case scenarios, the time complexity will be here O of n log n. And for average case also it will be O of n log n. But in worst case scenario, it will be O of n square. Let's see why is that. In best case scenario, let's assume this is our given data and we have to sort it using quicksort. So we will do the same process here, taking the first element as our pivot and then moving small elements to the left hand side and larger elements to the right hand side. And we have to do it recursively, so we will take 4 as our pivot in left hand side and 12 as pivot in our right hand side. And then again moving small elements to the left hand side and larger elements to the right hand side for both. Now we have to do this partition or decomposition for minimum 3 to 4 times in order to get our array sorted. So can we say that we are doing this partition or decomposition for log n number of times. So take a note here, we are doing decomposition for log n number of times. Now whenever we are doing this partition or decomposition, we are comparing our pivot each and every element in order to separate the smaller and larger elements, right? Which means we are doing n number of comparisons here. Now join both of these points. We are doing n number of comparisons for log n number of times, which means our time complexity here will be O of n log n. I hope it's clear. If you still have any doubt, you can ask in the comments. Same will happen in average case also. Now let's see the worst case scenario. Now assume your given array is already sorted, but for simplicity we always take the first element as our pivot. So in this case we will do the same, assuming 1 as our pivot point, and now to separate smaller elements in the left hand side and larger elements into the right hand side, we have to compare it with the rest of the elements in the given array. But since there are no smaller elements, so there will be no left hand side. Continuing with the right hand side, the next pivot will be 2 here, and then we have to compare it with all of the elements that are available in the array right now. Same thing we have to keep on continuing, and here if you see we will be having decomposition for n number of times, because you will be taking pivot 1, pivot 2, pivot 3, pivot 4, 5, 6, 7 and so on. Since there are no partitions like the best case scenario where we were having left and right hand side, so the decompositions are going to be O of n. And since with every pivot we are doing n number of comparisons, now joining these 2 points will give us the time complexity of O of n square. Now is there a way to improve this O of n square time complexity for worst cases? Well, we can fix it, but for that we need to pick the pivot point from the middle of this sorted array so that we can have equal number of elements in left hand side and right hand side. It will basically reduce the number of decompositions. But again, since the given array data can be sorted or cannot be sorted, it can be random also, right? So there is no guarantee that if we start taking pivot from the middle point, then we will have a better time complexity. So that's why for simplicity, we usually go with the first element as our pivot. I hope this part is also clear. If not, then you can ask in the comments. Alright, so that's all for the time complexity. Now coming to the space complexity, if you see with every iteration or every recursive call, we are separating our elements into arrays. There is no array that contains n number of elements, but we can say the arrays will have log n number of elements. So the space complexity will be here of log n. So that was our time and space complexity for quicksort, and thanks for watching.